Exponential decay exhibits a very similar formula to that of uninhibited exponential growth. It's actually exactly the same formula, except for there's a negative growth rate instead of a positive growth rate, and how that manifests mathematically is changing k to a negative instead. And if you were to look at, well, what's the derivative of such a function with initial population p0 e to the minus kt? Well, again, the derivative of p0 would, its coefficient would not affect it, and then we would take the derivative of e to the minus kt. Well, that would be exactly equal to itself. So just let me go ahead and sketch out my thinking. Whoops, I need to shoot, I'm on my tablet and it's not working quite right. There we go. I think we're good to go. But yeah, p prime of t, it's in green for some reason, but that's fine, would be p0. And then again, we take, well, e to the minus kt, the derivative would be exactly equal to itself. But we need the chain rule, so differentiating negative kt with respect to t would just be negative k. And basically what we get is the derivative would be equal to the population size times negative k. So what we'd see is our growth rate is negative instead of positive. Again, proportional to the original side based on the percentage factor of k. And again, it would be getting smaller and smaller over time. Or if you graph exponential decay functions, basically just with a negative exponent, it will have the same shape. It will just be looking like this instead. And this tends to model things such as imagine something dies and is naturally, imagine it laying on the ground, not to be morbid, but imagining the process for which is decaying and how much material is left over time. Decay tends to happen very rapidly at the beginning and then sort of slow down over time. And again, it's due to proportionality. The more of something there is, the more there is for it to decay. The less of it there is, there's less for it to decay. If you can imagine insect activity or whatever, it will slow down over time, meaning that it will last not necessarily indefinitely, but it will have this negative exponential decay. And this is very common in chemistry and physics and nuclear physics and such. Looking at decay rates of, say, radioactive materials or whatever, often it's described by what we call a half-life. A half-life is just a way of describing, well, how long would it take for that material to lose half of its amount? Again, usually in the context of exponential decay, since that is how materials decay. But let's look at example number 1. It says radioactive substances decay exponentially. Plutonium-240 is a nuclear isotope that undergoes spontaneous fission, which could cause problem with reactors. But say that we have 60 milligrams of plutonium-240 with a half-life of approximately 6,560 years. And basically, this is a very long time. It's sort of saying that it will, basically the longer the half-life means the longer time it will take for it to naturally decay. And being 6,000 years implies, well, if it starts with 60 milligrams, it'll take that long for it to decay down to 30 milligrams. Meaning it's going to last a long time. It's not going anywhere, for lack of a better way of saying it. And this is a critical problem with nuclear waste, is that it has very, very long very long half-life. It remains radioactive for absurdly long times, and it's very dangerous material that you don't want falling in the wrong hands. And for some reason, our best solution of how to deal with it is to go store it in the secret mountain somewhere, and it's not that secret. But anyways, I'm getting off topic. So mathematically speaking, you can always figure out the decay rate based on the half-life, using this formula. But it's sort of like how the doubling time is taking the ln of 2 divided by the rate. Very similar. You can find the rate by taking the ln of 2 and dividing by the half-life. And the same thing works for doubling time, for the record. But anyways, let's go ahead and... The first question is, how much plutonium-240 will we have left in 500 years? How about 5,000 years? But basically, if I want to create a model for exponential decay, I need to start with a formula. And so I need to know, well, how much did I start with? P of t is equal to the starting population, which we had 60 milligrams to begin with, E. And then the whole deal here is that K is equal to ln of 2 divided by the half-life, 6560. And we could approximate that with our calculator. the natural log of 2 divided by 65. 60 ends up being approximately, and again, this means times 10 to the negative fourth, which would be 4 decimal places to the left, 0.0001. Approximately 0.0001. And we'll go ahead and round to 3 significant figures just to make sure we're not overly rounding. Again, rounding is the enemy for accuracy. At the end of the day, these are just predictive models, but when it comes to online homework or whatever, just do your best to not round too much because it might make the answer fall out of the accepted range of the homework. Anyways, this would be our function which models the amount of plutonium we have left after T years. Again, where the time frame of T should match with your decay rate, since that was a year's in the half-life formula. This would be like a yearly rate, and so we're good using years here. So I could do P of 500 to figure out how much plutonium I have left after 500 and 5,000 years respectively. So after 500 years, I would have 60 e to the 0.000106 times 500. And that would be about, that's not right. It should not be more. I forgot my negative. And I did forget my negative when I was writing as well. And that's the key, again, obviously, between exponential growth and decay, is we need to have a negative for it to be decaying. If we don't have the negative, it's going to actually be growing by that growth rate. And I'll pretend I made that mistake on purpose. But I can quickly tell that that's not right because it was getting bigger. It should not be getting bigger. It should be getting smaller over time. And it will have approximately 56.9 milligrams. Again, we'll have the same units as we were dealing with to begin with after 500 years. So again, big problem, right? It's not going anywhere. It's not losing its radioactivity very, very fast. Now, some substances have half-lives of very, very, very quickly, like 1 year or 10 seconds or whatever, and that means, it's going to decay really rapidly. A lot of unstable materials actually have very, very short half-lives, meaning that they decay really, really fast, but not the case with a lot of types of nuclear waste. Anyways, and then we have 35.3 milligrams after 5,000 years, and we'd expect it not quite to be down to half, since the half-life is 6,500 years, but notice it's getting pretty close. And another question is, well, what if to get to a certain threshold, we want it to decay down to a certain point before we deem it safe or whatever? Obviously not the case with this material, but again, if we wanted to know how long would it take to get to a certain value, we could always plug that in and solve for T, because we know, well, the function is 60 e to the negative 0.000106 T. And I know that I want to know, well, what T value would it take to get P of T to 10? So I just plug in 10 on the other side. And that would, again, to solve this equation, we always need to isolate the exponential function first. So divide by 60, because that's just a normal multiplier, which would leave me with 1/6. And then now I have e to the something. I can always use the natural log to solve an exponential equation. So applying the natural log to both sides, this would be ln of 10 is equal to negative 0.000106 t, because ln is the inverse of e. And then I could divide by, now that it's just a normal equation, no more exponential, could divide by this 0.000106, and that would leave me with t is equal to that. So the natural log of 10 divided by the growth rate, and that would leave me with something very, very wrong. This should not be 10, this should be 1/6 again. Another thing about applied problems is we should always be able to figure out, okay, does my answer make sense based on, this should be a time frame. I'm expecting this to take a very, very long time, since, 5,000 years later, it still had 35 milligrams. It's going to take a whole lot longer to get down to 10. And a negative answer obviously doesn't make sense, but I forgot to simplify my and just, I was supposed to apply the ln of both sides of this equation, and I just forgot my divided by 60. So this should just be, everything I did before was right, except for this should be 1/6 instead, and that would give me a time frame of approximately 16,903, whatever, good enough, years. Similarly, we can apply the idea of the decay of materials to date how old something is. So, for example, this is the idea behind how carbon dating works. Obviously, there's a lot more science to it, but carbon-14 is a material which has a half-life of 5,730 years. Very long half-life, and the longer the half-life means that the less time something has had to decay. And like, imagine that you have an old dinosaur bone or a piece of parchment, and you want to know how old it is. You could estimate, well, how much carbon is left in this material, and compare it to how much carbon you would have expected to have it to have had when it was first created. Using, and again, we won't get into how you would even approach that idea. But let's just look at the math. So it says the percentage of carbon-14 within the remains of animals or plants can be used to determine age. Archaeologists determined that the wrappings from one of the Dead Sea Scrolls had lost about 22.3% of its carbon-14. How old was the wrapping? And obviously, dating old documents can be really important, because let's say we wanted to know if something is a fraud or not. We could, there's various techniques for determining how old something would be, but analyzing the carbon-14 particles is one. And you can actually date things using other things than just carbon, but it is one of the first ways that we've figured out to do this. And its long half-life and its prevalence in a lot of materials makes it a pretty good choice for doing dating of things. But anyways, how would we approach this? Well, again, it's going to be undergoing exponential decay based on the half-life. So we could start by figuring out, well, what's the decay rate? That would be the natural log of 2 divided by 5,730. And that would, let's go ahead and figure that out. The natural log of 2 divided by the half-life of carbon-14. It's going to be about 0.000121. Again, that would be negative when I'm plugging it into the formula. And then we would have an equation which goes the amount of carbon is based on the initial amount times e to the negative 0.000121 times t. Now, the other thing about this question is, notice we're not given a particular amount. Like in the previous example, it told us we started with 60 milligrams. And that was our P0. Here we don't know how much it started with, which is obviously the problem, because we didn't have, we're trying to figure out how old this is. We weren't alive potentially when the Dead Sea Scrolls were written. So how would we know how much it started with? But that's kind of where it comes down to, well, how much is left? It's lost 22.3% of its carbon-14. So you could actually use like an amount, but here we can use a percentage, because we're assuming that it started with its full 100% of carbon-14, and it's lost 22.3%, implying that it has 77.7% remaining currently. And 777.7% is a heck of a coincidental percentage for this, which I find to be quite interesting. But of course, basically 100% is equal to 1, where we could basically divide that to the other side. But if we know, this is how much is remaining, really that's just, if I write that as a decimal, that'd be 0.777 left, equal to 1 times e to the negative 0.000121t. Basically, the initial population, I'm assuming that's just the full amount, so on the other side is percentage, and that's kind of the deal. Like, also looking back at the equation that we just solved a little bit ago, notice that what ended up happening is I took the natural log of 1/6. Well, that was actually the fraction of how much was remaining, and that's the general idea here. You take the natural log of how much is remaining, the natural log of both sides, and that will be the first step to figuring out how much is left. In this case, you take the natural log of the percentage remaining, and that will, again, ln and e will cancel each other out, which is the reason why we'd all do this. And then we could divide by the rate of decay. So here time would be equal to the natural log of 0.777 divided by negative 0.0000121. And this should approximate the age of the Dead Sea Scrolls. ln of 0.777 divided by negative 0.000121, which comes out to be time is approximately 2,085 years. And then we could see, well, does that come out to where I expect it to be for the age of this document? How close is this to what it should be historically speaking? And again, this is just an example. We don't need to look into the correctness of these numbers or anything, because as I said, it's not always an exact procedure. Because again, how would we have known exactly the percent that remains in there? But again, that's more on the scientific side. But mathematically speaking, the rate of decay of materials is well established, and we can use that to predict things like how much will be left, and use the current projection to figure out how old something is.